Now we have a set of 3 lessons which go through in somewhat less detail the other classifications. We did sort of in some detail the 2 basic database classifications, SQL and NoSQL. Now we come on to the other use case classifications. Um, well, we pointed out the geographic information system classification, and that's very important because so much big data is labeled by space, 3 dimensions, and time, possibly just space, but typically space and time. That space and time can be on the Earth, microscopically in the atom, macroscopically in the cosmos for astronomy. And when you have things organized by space, you know that different points in space are distinct. And if they're a long way away, that means something different from if they're close to each other. So a geographical information system is designed to display spatial, also called geolocated data, so that you can get an insight as to what's going on by just browsing, as you're very familiar with Google Maps or Google Earth or Microsoft Virtual Earth. Use cases 43 and 44, which we went through, which were the polar science and earthquake science applications. They have map-based illustrations. Although in some physics cases, we don't have GIS because if you're dealing at the very shortest scales, a map is not so useful. So particle physics does not use that. And obviously, even when you're doing material science, then you will have simulations which would need to be visualized in 3 dimensions, but you wouldn't actually use a GIS. GIS for the special type of 3-dimensional applications where the sort of the view of a map is a useful way of thinking. Noted here the Open Geospatial Consortium. It's enabling these GISs to work well by setting standards and establishing methodologies so that the different producers and owners of geolocated material can present that material in a way that can be used. So you can have the same map with data from NASA, Google, US government, your favorite foreign country, and so on. Here's on the right here, we have a nice example from use case 44 of an earthquake simulation. This is the QuakeSim website, which has a lot of information predicting or looking at the consequences of earthquakes. And one signature of an earthquake is GPS sensors. Their movement, which they detect, can be a signature of an earthquake. And here we have a map with little symbols as to where the GPSs are. If you click those symbols, then you'll get a lot of information, including the actual time series from that GPS. Then over at the top left, we get something different. It's still 3 dimensions, but it's a typical 3-dimensional simulation. This is use cases 11 and 12, the material science ones, where here we have a nanomaterial, and we still use 3D simulations, but not a map. We just simulate the structure of the material. An exciting case, which I really like, is the Internet of Things. Remember, there were 24 to 75, or maybe if we take all devices, including those which are not on the internet, 200 billion devices by 2020. And here we have a sort of schematic of how those devices are arranged. You have a cloud. The devices communicate via the internet with the cloud. The cloud does the processing. They accept the data like the Connect. They get the data, the images from the Connect, and processes them and make decisions. In the case of the one of the stuff presented here on the left, this is associated with actually use case 43, the Croesus project, where you have radar sensors, which are large. These are essentially large internet things, um, and those, in fact, we see I put in the cloud, sensors as a service, the actual signal processing for that problem. And you could use MapReduce here to do the processing of all possible sensors. You won't do a Lego robot, a smartphone, and Connect all at the same time, but you would do groups of them and integrate them and fuse them and all sorts of things. So clouds, as we mentioned, are perfect for the Internet of Things, because the easiest thing to do on a cloud is to have a single virtual machine without any direct, highly correlated parallelism, and exactly what the Internet of Things does, because everything on the Internet of Things is relatively small, and therefore it is natural to associate it with a single cloud process in a single virtual machine. Quite often, such a virtual machine, when you have a sensor that's only producing data at once a minute or something, or once a second, then it's a waste for that virtual machine just to process one sensor. It can probably do 1,000 such sensors or something like that. And here we have this model underlies robotics, and actually underlies the smartphone revolution. That's why smartphones are smart, because of the cloud, and because you have this model of cloud-controlled things. So here it points out the cloud records the data, controls the devices, essentially becoming a point of source of intelligence, either by doing sensor-specific computations or just accessing the world. Your smartphone, when it brings up a browser, is using the cloud to search the world. This is a diagram I've often used, and it illustrates quite a lot of things. As I'll point out later on, it illustrates data fusion. Around the top, the left, and the bottom, we have typically sensors, or maybe other so-called services. A service is anything which receives messages and spits out messages, anything electronic. And these sensors and other services, and Hadoop clusters, and grids, and compute clouds, and webcams, and telescopes, and databases, large LHC detecting device, ... satellites. They pour out data. Those data go through analytics. Those analytics live in so-called filter clouds. A filter is here actually the same word as map. In MapReduce, you could actually call MapReduce filter reduce. Filters are actually a somewhat more common term in the signal processing sensor world. Filters take data and make new forms of data. And in fact, as we've discussed in the introduction to data science, you always have this pipeline. Raw data goes to data. You sometimes combine those two. You always have data goes to information, where information is the uncontroversially processed version of data. Knowledge goes to deep analytics, the machine learning built in, where you can often distinguish between knowledge and wisdom. And then you have sometimes at the same level as wisdom, decisions. And this pipeline is shown on this figure. And it's just data pouring from everywhere, getting put back into itself and put back into the cloud, into different clouds, pouring through services, which can be a single service, or here we have the concept of a discovery cloud, which is integrating things together. And then we have here up at the top right, we have the people with the portal, which is receiving this information, which is then received in a fashion which is fused to optimize the chance that the person using the portal will be able to make good decisions and good discoveries. Here's an example of a fusion or a sensor control interface, which we built a few years ago with a friend of mine, Alex Ho. Um, and we have Lego robots, actually some in Hong Kong and some in this time at the conference in Irvine. And these are actually geolocated, so it's actually got GPS devices which are then read out and then they're recorded automatically on this portal. This is an example of the Discovery portal. On the right here, we have the list of all the various sensors we're looking at. We have various commands on the left, and then we have these displays, which are the outputs of the sensors or data about the sensors. Here we have webcams. Obviously, we have webcams sitting on Lego robots and running around and taking pictures of other Lego robots and so on. And so this is an example of the type of discovery portal that you would want. In this case here, this was work done from the Department of Defense, the U.S. Air Force. This is how you would make your decisions, a type of a vision as to how you would design the interface to large-scale sensor systems. These divisions into use case classifications 1, 2, and 3 are slightly ad hoc. They're just to give you a break so you don't have to listen to me talking too often. We really need to do MOOCs differently. In fact, I think other more professional companies do this. We need to distinguish the actor who presents the MOOC from the scientist like me who prepares the MOOC. Here we're making them the same thing, which is traditional in universities, but that's certainly not how recorded books are done. It's not how movies are done. You have writers are separate from actors and so on. Anyway, you unfortunately have to listen to me at the moment, and we don't have a nice actor or actress to present it to you. Okay, so you do get these breaks here. So here we have a break. Enjoy it.